All right, here is Unit 2, Topic 2 on intramolecular force and potential energy. So we are going to analyze potential energy diagrams, which are graphs, in order to compare relative bond strength based on the bond type and length. So this section is really dealing with covalent bonds and some of the forces that happen within them. So first we need to define just a few things. First is bond strength. So when we're looking at a covalent bond where atoms are sharing their electrons, the attraction between those bonded atoms indicates the strength of the bond. So if we have a greater attraction, it means we get greater strength in that bond. And remember, the attraction, the force of attraction, is based on a couple of things. It is based on or can be influenced by charge, which doesn't really happen much here, but it can also be influenced by the distance between the atoms. And this is really where we're going to see more in this section. So then we have bond length, is the distance between the nuclei of two atoms, and it depends on the number of bonded electrons and the radius of the atom. So if we look at bond length here and the number of bonds between two atoms, we can see that the bond length is indicated in PM, that is picometers, and those are, they're smaller than even nanometers. So we've talked about nanometers before. 1,000,000,000 nanometers are equal to a meter. So you can fit 1 billion nanometers in a meter. A picometer is even smaller than that. It's 10 to the 12th picometers is equal to 1 meter. So even smaller. So the length between two atoms is measured in picometers, and we can see as we go from a single carbon-carbon bond to a double carbon-carbon bond, where it's sharing 4 electrons now instead of the 2 electrons here, they share 4, our bond length decreases. As we go to a triple bond where we share 6 electrons, our bond length decreases again. And so the more bonds that are shared between two atoms, the shorter the bond length is going to be. Okay, the shorter the bond length is going to be. We can also look at the radius between two atoms, or of the two atoms. So here we've got the same element on the left, carbon in each one, and then we're looking at the radius of fluorine, chlorine, bromine, and iodine, our halogens that are in group 17. So they are lined up from fluorine to iodine. So our atoms would get larger going down that group as we add more energy levels. We can see that as those energy levels of our second element, our halogens, are increased, the bond length also increases. Okay, so the key takeaway from this is that when we have a shorter bond length, we have a larger strength in the bond. Okay, the closer those atoms are to each other, the stronger that force of attraction is, right? Smaller distance, greater force. So we get a greater strength in the bond. So short equals strong. So 2 ways to make it short are having a small radius or increasing the number of bonds between the two atoms, having double versus or triple bonds versus single. We can shorten that bond length and strengthen that bond between those atoms. So what we're going to look at with the strength of bonds is what's called potential energy diagrams. So potential energy diagram represents the distance between the atoms versus the potential energy of the atoms. So down here on the bottom, the x-axis is your internuclear distance, the distance between the two nuclei of our atoms, okay? So that distance between. And we're looking at the potential energy of those bonds, okay? The goal of atoms that are bonded is to minimize or make it the smallest potential energy possible. This allows the forces of attraction between the atoms to equal the repulsive forces between the atoms and become stable. So when atoms are pushed together, we can see up here, it reduces the distance between them. And if we reduce that distance too much, the electrons become too crowded, too close to each other, and so they're going to start repelling each other. Okay, so we have too much repulsion here up at the top. So we can see our graph shoots up over there on the left. If the atoms are pulled apart some, the attractive forces will be too strong and it will pull them back together. So if our atoms were, say, here and they were still overlapping a little bit but pulled further apart, they're going to want to attract together because they are more attracted to each other and get to that perfect bond length there. But if we pull them apart too much and they don't have any overlap between the atoms, between the electron clouds, then they're going to have no attraction and those atoms are just going to separate from each other. So a bond is created when we get this perfect distance between the two atoms, where the protons of one atom are attracting the electrons of the opposite atom, and we have that attraction occurring, and the electrons aren't too close to each other that they're repelling each other. So we have the equal attraction and repulsion, and it balances out to create our perfect place on our diagram here. All right, we're going to take a look at an interactive here that looks at these potential energy diagrams and the distance between atoms. We'll just mess around with it and see a few things. So we have one atom, these are argon atoms, so one is pinned in place, so it's stationary, and the other atom we can move. As we move the atom, you can see on the graph that it also moves, indicating that bond between the two atoms. So we can see as we move it, as we move the atoms closer together, we're going further to the left on the graph, and as we pull them apart, we're getting further to the right. Okay, so we're changing that distance between the atoms, so we're moving along that x-axis. So as we have less distance, we're towards the left. As we have more distance, we're towards the right. So we can also let go of the atom, and what we can see is that those atoms are attracted to each other and kind of almost bounce off of each other. But that the atom doesn't just fly away. There is this attraction between them. So that attraction is really what's key here. So we're going to show what's going on between these. I'm going to show the forces that are happening here. So in yellow, between the atoms, we see the attractive force. As they get closer, that yellow arrow grows and they become more and more attracted. But as they get too close to each other, that pink arrow gets really big, and that represents the repulsion or repulsive forces between the atoms. So I'm going to slow this down and bring them together slowly. So again, we start to have we have more and more attraction as we bring them together, but as those clouds get closer to each other and we have that overlap, we're going to start to have repelling between those electrons. When the repelling, the pink arrow gets bigger than the yellow arrow, then the atoms start to move apart from each other and they are repelled. We can have the atoms get so close to each other and that they repel and the atom flies away. Okay, when the forces total out at zero, where there's not more attractive or more repulsive forces, the curve bottoms out, and that is the perfect distance between those two atoms. Okay, and we would measure that as the bond length. Okay, so atoms are trying to minimize their potential energy. They're trying to find a balance between the attractive forces where they're pulling together and repulsive forces where they're pushing apart. Okay, and they will always try and find that happy medium with their bond length. We can also look at some different atoms. So if we change from argon, which are pretty big atoms, to neon, we can see the electron cloud shrinks and our potential energy also goes down. It gets more shallow in that curve. So again, we have the total repulsive forces when we push them together, and we get attractive forces when we pull them apart. But notice that those little green arrows are not as big as the last atom. We still get that attraction, but it's much easier to kind of pull them apart and not have them attract as much, right? We have that little smaller change in potential energy. We can change something to an element like oxygen, and you notice that our curve changes. I have to zoom out on my curve, and that's because oxygen has a double bond, so they have more attraction between those atoms. Notice how much they want to attract to each other, right? They have a double bond, so they're sharing 4 electrons. That's really strong between them. And it's a lot harder, or when we push them together, they're going to repel more, and we can shoot that atom right out of there. So this just gives you an idea of what's going on between our atoms. And we're going to analyze these graphs and see how they change when we change the distance between our atoms, and we change the number of bonds between our atoms, and that sort of things. So we've seen a little bit on how the different atoms can affect the graph. So we're going to focus in on just the number of bonds. So if we have the same element, again, looking at this carbon, 2 carbon atoms bonded, we can look at a single bond versus a double bond versus a triple bond. And we're going to see how the graph, the potential energy diagram, changes. So since the bond length decreases as more bonds are formed between the atoms, the graph will also change. So first, the graph will shift left due to the distance being reduced between the atoms. So again, our x-axis is that distance between the atoms. If our distance is decreasing, then our atom is moving closer to the left-hand side, closer to our y-axis. So we can see that our place where the atoms are, this is our bonded atoms, that lowest point there, it's moving to the left. So it's showing that distance between the atoms decreasing. Okay, so we can always judge the size of the bond length based on these graphs. So that's one thing we can get from the graph. The second thing we see is that the curve will dip lower. And this is due to the increased attraction between the atoms, and this increases what's called its bond energy, okay? So the energy it takes to break these bonds. So since this bond is shorter, it's also stronger, so it takes more energy. This line here indicates energy. So it takes more energy to break that bond, to get it where those atoms are separated from each other. Break that bond. All right, when we have a shorter distance, like let's look at our single bond, shorter distance is going to be a weaker bond and require less energy to break that bond. So it has a lower bond energy. So this has low bond energy, and our triple bond has high bond energy. We are going to look later at actually looking at bond energies, values, and calculating what the bond energy is of a compound. How much energy does it take to break all the bonds in the compound? But for now, we can use these diagrams to help us indicate which bond is easier to break or which bond is harder to break. It would be easier to break a bond that has low bond energy and harder to break a bond that has high bond energy. So we can also look at the length of the bonds, not just the number of bonds as well. So if we compare different elements, so this one shows element X, Y, and Z. Each of them are 2 of that element bonded together. The shorter the bond length is, the more left that dip is going to be. Remember, our optimum bond length is right here in the dip. That's where we're analyzing our chemical. So the one furthest to the left is going to be element X. So it would have the shortest bond length. Then we would get to element Y and then Z. So our longest would be element Z, and Y would be in the middle. Okay, so we can analyze the bond length to see what's happening, or analyze the graph to see what's happening with the length of our bonds. We could also go ahead and look at this graph and analyze the strength of the bonds and see which one would have the greatest bond energy or not. So if I took this away, all of our info, we could look at the strength of the bonds. So if we went, let's go weakest to strongest, looking at these, we would want to look at how far down that element is in the dip. The strongest one would be furthest down, so that would be element Y, and our weakest one would be X because it's the shallowest dip, and then element Z would be in the middle, right? So we can analyze this graph for two things, both the length of the bond and the strength of the bond. So these graphs indicate a lot about the bonds between atoms. So let's just take a look at a couple of example questions to give us an idea of how questions might be asked for this. So here's two different questions. I kind of overlapped them. So the first one, the approximate bond length of the atom shown by this potential energy diagram is. So this kind of question is asking you, do you know where to read the graph, essentially? So we want to read it again at that lowest point at the dip. Our bond length is indicated by our x-axis. You can see that this unit A with a little circle on top, that is angstroms. That's another way they measure the size of the bond length. Instead of picometers, they used to use angstroms, and it's just a very small unit of measurement. But here, the unit doesn't really matter. We just want to be able to read the graph. So we're between 3 and 4, so D is definitely out. We are more than halfway, so A is definitely out and C is out. So B has to be our closest one, 3.75. So that is the length of our bond. We just want to read it at the dip. So it's basically, this question is really saying, do you know how to read this graph? Okay. Number 23 over here that I pulled up, consider the potential energy curve depicted below, which represents covalent bond formation in bromine. So this is indicating bromine, Br2, forming. If you were to add to this diagram a similar curve for chlorine, so this is for bromine, we want to look at that for chlorine. It says it would feature a potential energy minimum represented by point C, that is blank, and shifted blank relative to the curve for Br2. So it's asking us to compare this graph to what it would be for chlorine. Well, the big thing we want to think about is their relationship on the periodic table. They are both halogens, so they're in that last, or that group 7. Fluorine, chlorine, bromine, iodine are halogens. So chlorine is a smaller atom, indicating a smaller radius. Okay, so the first thing is point C will be shifted left to a smaller distance. So we can start eliminating energy minimum represented by point C, that is blank and shifted left. So we want to take out all our options that shift right. Okay, we want shifting left. Then we need to think about what will happen to its energy. Well, if it's a shorter bond, the atoms are closer together, so it should have less or require less energy. So it should be that our point C is also shifted up. All right, we're going to shift it left and shift it up. So the key here is saying higher, less negative, or lower, more negative. So this is 0, and this is our negative side, our positive side. So we are going less negative. So we want A for our answer. Okay, so that's how we would judge this type of question and how we would answer it. All right, let's try another couple of questions using this graph. It's a little blurry, but it's what we can find. So it says, which atom forms the weakest bonds? So if we look at this, we want to look for our weakest bonds, or ones that are easiest to break. So think about it, see if you can pick which one it is. So for this one, hopefully you picked that it was curve B here because it has the lowest potential energy, or excuse me, the least negative potential energy. It requires the least energy to break its bond. So that would be B because it has the lowest potential energy. All right, number 2, which curve represents an atom pair that forms bonds with the largest atomic radius? So pause for a second, think about it. All right, hopefully we picked letter A. So curve A has its lowest point is furthest to the right, indicating that it is the greatest distance between the two atoms. And the last one is a true/false. The bond formed by atom pair B requires less energy to break than the bond formed by atom pair C. So we're comparing curves B and C, and it's saying that the atom pair B requires less energy to break the bond than the bond formed by pair C. So think about it, see if you pick true or false. All right, hopefully we picked true on this one. Because it is curve B is higher up than curve C. So curve C is going to require more energy to break its bond than curve B will. Right? All right, here's one more question. Why don't you take a minute, look at it, pick your answer, and then I'll go over it. So pause it and think about it, and then we'll go over it. All right, so our question, the plot below shows a potential energy curve of two diatomic molecules, diatomic meaning made of two atoms, and they are AB and CD. Which one is a false statement? So our two chemicals, we can see that here's our 0 line, so we can already see that AB is a longer bond length, but CD requires more energy to break its bond because we have a greater distance there to the 0 mark. So it says CD has a stronger bond. That's true because it has lower minimum energy than AB. That's true. CD has a weaker bond because it has a narrow energy curve. That is not a true statement. And CD has a shorter bond length. That's true because its energy minimum is at a shorter internuclear distance than AB. And that is true. So B is a false statement. How skinny the curve is does not indicate a weaker or stronger bond. All right, hopefully this gave you a good overview of potential energy curves and potential energy diagrams and an idea of how bond length and bond strength and the number of bonds influence each other. So we're going to be using that information to do some practice with it. Let me know when you have questions.